Ah, right. Sorry. And the microphone's not plugged in, but there's the formula. So I've written a formula. I'm going to do an example, and then you can have a go. Okay. There we go. Microphone light is on. That's a good sign. All right, so that's line integrals and work. So work is the line integral. Okay, that's the basic formula. That is the same as that. Okay? Which is also the same as Q dy plus R dz, where P and Q and R are the component functions of big A. So I get easy today. I woke up at 2 o'clock and went back to sleep. Round about the time the alarm went off, I started to feel sleepy again. So now I'm running around like a zombie. We're basically looking at, so it's work, which is essentially a force times a distance, but in this case, the force is changing over the distance, and that's why we have to take the distance that we have to take the path that the particle is moving along and chop it up into very little bits and basically work out all the little bits of work. So it's your basic work formula of a force times a distance. But because the force is a function of position along the path, we have to do that chop it up into little bits thing and add them all up, and then that inevitably becomes a line integral. Yeah, because we're only really considering a particle moving along a path, and we want the work done basically that is done as it moves through some sort of force field. So I'm not being very clear. Question? No, okay, the question, it has to be a line integral. It has to be a line integral because it's all to do about linear distance. And because it's a line integral, that then dictates that you have to deal with parametrizing your curve and integrating with respect to the parameter that you use to parametrize your curve. Okay. I am going to demonstrate with exercise 10 in your handbook, if I'm not mistaken. Yes. The 4xy, 3x squared, calculate the work done in moving a particle from 0, 0 to 1, 1 along y equals x and then y equals x squared. Okay, so I'm going to work along two different paths. There's the line segments, but then there's also the piece of parabola. I'm going to call the line segment C1 and the piece of parabola C2. Okay. One, let me parametrize it. It's going to simply be T2, where T goes from 0 to 1. And curve 2 is going to be my paper on vector notation has been accepted for publication. I'm very excited. I'm sure you will be equally excited. I'm sure vector notation makes you just as geeky as I get. And on that note, I'm going to be disappearing today. If you look for me today, you're not going to find me because I need to do revisions to that particular paper, and I can't do that anywhere close to the internet. Because otherwise the internet just eats me alive, and I just check email and watch the news and stuff all day long. So you won't find me today. Okay, work done. So work. I'll call them work 1 and work 2 along the 2 different parts. Question. That is T and T squared. This is my way. So I think the T squared is fairly good. It's the T that I have. Okay, I'm very woozy today, so let me go slowly so I make sure I don't make any mistakes. It's y equals x squared. So if x is t, then y is t squared. Yes. Okay. If you notice me make any mistakes, please do let me know. Okay. So I'm going to work out the work along curve 1, and it will be the integral from 0 to 1 of f. So I'm going to write f now, but instead of x and y, I'm going to write the parametric expressions for x and y, which along curve 1 are just t and t respectively. So it will be 4t squared and 3t squared. I'm going to dash it with and it's dt. Okay, so let me do a little dot product. It'll be 4t squared plus 3t squared, so it's 7t squared. And then that's just single variable calculus. That's just 7 over 3t cubed from 0 to 1, which is 7 over 3. Okay? Let's have a look. Just in order to save space. Okay, I'm rubbing this out, but not because it's me. I just want to scrunch it up a little. Okay, I'm just trying to make a bit of space there. I'm going to do work 2 alongside rather than below. It'll also be f dotted with r dash of t dt along C2 this time. The limits of integration are still 0 to 1, simply because of the way I've parameterized my curve. Different parameterization might have resulted in different values of t. F will be, okay, so this time I'm plugging t where there's x and t squared where there's y. So f is 4xy, so it's 4 times t squared, so it's 4t cubed. And 3x squared will be 3t squared. And I'm going to dot that with r dash, which is 1, 2t dt. Okay, so it is slightly different. Started off the same. That is going to be 4t cubed plus 6t cubed, so it's going to be 10t cubed. So am I right? 4 plus 6, and they're both t cubed. Yes, 10t cubed. So that becomes 10 over 4t to the 4 from 0 to 1. That's 10 over 4, which is 5 over 2. Okay, thereby demonstrating that the work done along different paths is typically different. The path matters. It's not just the endpoints that matter. However, you'll notice that 10 has a part B, and in part B, it suggested that you do all of this again, except with a slightly different. Instead of 3x squared, we have 2x squared. And what you'll notice, I'll work through it, but what will happen is that our work 1 and work 2 will actually end up being the same. And that's going to provide me with a little bit of a segue into the next section that we do, which is conservative vector field. But let's just demonstrate. What is it? 4xy and 2x squared. So what difference is that going to make? Work 1 is going to be very similar to the above, except with a 2 where there was a 3. And so instead of 4t squared plus 3t squared, I'm going to have 4t squared plus 2t squared, which is going to, so I'm skipping a step here because it's so similar to the one above. I'm going to end up with 6t squared instead of 7, because it won't be 4 plus 3, it'll be 4 plus 2. So that'll be 2t cubed from 0 to 1, which will be 2. I did skip a line there, but I'm hoping that it's a pretty obvious line because of the previous calculation. Work 2, similar. There's a 1 there, there's a 2 there. So let me go back. I think I forgot my subscripts and the R's just now. A 1 and that should have been a 2. Okay. And instead of 4t cubed plus 6t cubed, I'm going to have 4t cubed plus 4t cubed. I'm going to have 8t cubed dt. Do you see that? The line is right at the top of the screen over there. Instead of a 3t squared, there'll be a 2t squared. So when I do the little dot product, I'll end up with a 4t cubed plus a 4t cubed. Gives me an 8t cubed. So that will be 8 over 4. There we go. And in this case, the work done is the same. Now, that could just be a coincidence, but in fact, it's not a coincidence. It's because of the nature of the big F. Big F actually is something fairly special called a conservative vector field, which I'll get onto before the period is out. But for now, why don't you give just simply calculating work a try and try. You try number 11. You've got a force field. You're going to have to parameterize. If you can also so one sheet of LC plus a half E squared minus a half E. Okay, all right, so let's work that there are particular kinds of vector fields that are or there's a certain kind of vector field that's of particular interest in these sorts of problems. And those vector fields are called conservative vector fields. Could you please keep quiet? And path independence. Ooh, that's a long heading. There we go. It's kind of a subheading underlining course. So now let's think about scalar functions. In other words, z equals f of xy, or w equals f of xyz. So it's a function. It's x squared plus y squared. It's x squared times y. It's sin x plus e to the y. That sort of thing. A scalar function. If f is a scalar function of 2 or more variables, then we can find its gradient vector. However many variables it has. If it's got 2 variables, then there are 2 possible derivatives, and we'll have a 2-component vector for the gradient function. If f is a function of 3 variables, of course, then there are 3 possible partial derivatives, and then our grad will be a 3-component vector, and so on for higher order functions. We call that grad or gradient. Or, in fact, the gradient vector field. What term we've used, I can't remember. But it is, because it's a vector that has as its components little mini functions, and hence it's a vector field. Because your input is vector and your output is also vector. Okay, for example, little in grad F, so just to remind you of what grad is in case you've forgotten. Okay, so your gradient vector field is simply the vector that you get if you cluster together the partial derivatives of the function with respect to the variables that it's a function of. Okay, so What I had here was I had a scalar function and I worked out its grad. You can kind of sometimes do the opposite. Given a vector field, you can interpret it as a gradient and you can figure out what little f you differentiated in order to get that vector field. And sometimes you can do that and sometimes you can't. And if you can do that, you call the vector field a conservative vector field. And if you can't do that, you say it is not a conservative vector field. So given a vector field f, it is called a conservative vector field. I'm not sure why. It's actually conserving something. I suppose it's related to the path independence. Anyway, so I think it's a rather odd adjective, but anyway, it's called a conservative vector field. If there exists a function, any function, which I'm going to call little f, such that grad of little f is equal to big F. We call little f a potential function for big F. Oops. A potential function for big F. So there's some new terms there. Conservative vector field is a new term and potential function is a new term. Okay, I'm going to do a page turn, but don't worry about it. I'll scroll back up again. There we go. It's quite an easy concept. I'll demonstrate and you'll see it's really not that big a deal. And conservative vector fields are really nice. If you're doing a calculation involving a conservative vector field, there's all of a sudden a whole bunch of things that become simplified. And that is present in one of those decision trees. The word decision tree noted one up. You see the two little questions that you ask yourself. One is the C-post curve and the other is the conservative vector field. And if the answer to question 2 is yes, yeah, pretty much simple. Basically. Okay, alright, let me demonstrate with exercise 12 that this is not such a big deal. It is which of the following vector fields are conservative and what are their potential functions? Now, there is a sort of a trick that you can use to determine whether a vector field is conservative, but for now, we're just going to do it by inspection. So basically what you do is you ask yourself, does a little f exist such that the derivative of f, catch up with me stylus please, such that the x derivative of f is cos x and the y derivative of little f is e to the xy. That's what we're asking. Is there such an animal that when I carry out those derivatives I get cos x and e to the xy? And the answer is going to be no. There is no little f that makes that happen. Because if I differentiated, you know what happens when you differentiate e to the power of a function. Cos x is not the problem there. It's the e to the xy that's the problem. That's right. Because if we differentiate e to the power of a function, we get e to the power of that same function times by the derivative of the function power. That's Taylor for you. So if the y derivative has an e to the xy in it, it must mean the original little f had an e to the xy in it, which means the x derivative would also have had an e to the xy in it, and it doesn't. So there is no little f that could make these derivatives happen. F is not. So you can do it by inspection. There is a trick, and I will talk about the trick. But for now, I just want you doing it by inspection and just seeing that you just need to be logical about it. Questions? That's a sound sign. I know that there is no such little f. So it's not that little f doesn't have an e to the xy. It's just that there is no little f. Sorry, there you are, right? You hear the voice. Because you can work backwards, you can say the y derivative has e to the xy. I know how differentiating exponential functions works, so I know that if the y derivative had an e to the xy, little f would have had to have an e to the xy. But it follows then that the x derivative would also have had an e to the xy in it, and it doesn't, so there's no such little f. There is no such thing. There is no such thing. It is not possible. Question. Because you know how to differentiate e to the x. Okay? Back in single variable calculus, if you were differentiating e to the power of f of x, you get e to the power of f of x times by f dash of x. That's chain rule. That's how you differentiate exponential functions. So when you differentiate an exponential function, your derivative always has that same exponential function in it. And so you can work backwards. You can say, if my derivative has an exponential function in it, then my original must have also had that same exponential function. Exponentials are like that. They just don't go away. They're very invariant things. Yeah. Yeah, I suppose you can think of it as a derivative matrix where there is only one function that you're differentiating, and hence it's a one-row matrix. Hence a vector. Yeah. Question? Because if we ask ourselves, what did I differentiate with respect to x, because it's the first component, to get cos x, our answer would be sin x. Okay? And sin x clearly, when you differentiate with respect to y, gives you 0. So we could deal with the cos x. We could think of a little f. We could think of a little f that gave us an x derivative of cos x that did not contradict or did not conflict with our y derivative. But we cannot think of a little f that gives us our y derivative that does not conflict with our x derivative. Does that make sense? What else is there to say? Okay, so if the x derivative of little f is cos x, it implies that f of xy must have a sin x term in it plus some mystery function. Okay? If the derivative, the y derivative of little f is e to the xy, it's going to have an e to the xy in it. Over x, in fact. Because if we differentiate little f with respect to y and get e to the xy, then I must have started off with the term e to the xy over x. Okay? So I could say, okay, well then my little f must be the sum of those two terms. It must be sin x plus that exponential thing. But it can't be. Because if little f had that exponential thing in it, that exponential thing would have appeared in my x derivative as well, and it doesn't. So there's no such little f. There is no little f whose grad is that big F. It's impossible. And that's fine. That's not a problem. It just means a big F is not a conservative vector field. Cool, it's fine. Most vector fields are not. It's only special cases that are. No such little F is possible. Oops, okay. Let's look at B. B has minus sin x minus sin y. In other words, we're asking, is it possible to find a little f such that its x derivative is minus sin x, please keep quiet, and its y derivative is minus sin y? is it possible to create such a little f, to design a little f that makes that happen? And the answer is yes. Because we can design little f to be cos x plus sin y. No, cos y, sorry. Thank you. Thanks for keeping an eye on me. Because that'll totally work. Because when I differentiate that little f, the cos y term just doesn't even, it differentiates to 0 in my x derivative, and the cos x term differentiates to 0 in the y derivative, and my two derivatives will simply be minus sine x and minus sine y. So therefore, f is conservative. And this thing is its potential function. And C is f is a good friend for xy to exclude from exercise 10b, and I'm asking, is it possible to find a little f such as x derivatives for xy and its y derivative is 2x squared? So you think, okay, I differentiated with respect to x and I got 4xy, so what can I possibly have started with? I would have had to have had 2x squared y. 2x squared y would differentiate with respect to x to give me 4xy. Okay, but what does 2xy differentiate? There's a y in there. So it's clearly going to contribute to the y derivative. In fact, it's going to contribute to 2x squared to the y derivative. Hey, I've got what I want. You're working backwards. Absolutely, you're working backwards. You're saying, this is the result of the derivative. What did I start with? And that will give you what you started with. So f is conservative. Question. Yes, yes, it is a potential function because you could have a plus constant. All of these could have a plus constant, so there's technically infinitely many potential functions. I can't think of a single occasion where we do actually work with the plus constant. We always trim it down to its absolute bare essentials. But yes, it's a potential function. Okay, you give it a go. Time number 13. You've got 3 minutes before the end of the period. And I think once again it's true that